Hi, this is an AP chemistry video. This corresponds to our textbook 6.2 Enthalpy in Calorimetry. Um, so this part here is just me kind of talking. It's not something you really need to know, but um, most of our reactions, like when in our labs, are not at constant volume. We always have open test tubes and containers, but they do have constant pressure. So ultimately, we have something we call enthalpy, which is the letter H, and it's kind of a corrected way of calculating internal energy by using enthalpy um, at constant pressure. So basically, enthalpy change is equal to the heat at constant pressure. And remember, heat is just the amount of energy that is either absorbed or released. So let's do a problem. This is a problem where we know the enthalpy change for this reaction is negative. So we know it's exothermic. So that means energy is, this is methane, by the way. So burning or methane is going to give energy to the surroundings. So the energy is going to come off. So sometimes we write that value into the reaction. And we do that, when we do that, we do write it as positive because what we mean is, okay, I'm making carbon dioxide, 2 waters, and I'm going to be giving off 891.1 kilojoules. So that's always per 1 mole of the hydrocarbon right now. And we want to see, what if I have a gram? So this is, I would take your grams of methane and convert that to moles of methane. And then we know that for every 1 mole, we're going to have 891.1 kilojoules. So 1 mole of methane. So just realize this comes from that coefficient. And you can give this a negative value. You can also just give it a negative value at the end because that means that energy is being released into the surroundings from the system. So in all, our enthalpy change, which is the same as the Q at constant pressure for this reaction, is negative 55.5 kilojoules. So next question is the same reaction. And now we're going to look at, instead of an amount of grams of the methane, now we have a volume. So I know the volume, and this only works because it's a gas. I know pressure. So I would want to convert this to ATM because I'm going to use PV equals nRT. So if you understand that, then pause the video and try the problem and try to do it. So you're going to solve for moles of methane, and then you're going to do the mole energy ratio like we just did in the previous problem. So this ends up being 9736, blah, blah, blah. And then my temperature is 25, which would be 298 Kelvin. So plugging into PV-nRT, we're going to take our pressure, multiply it by the volume. Oops, that's times 10 to the third liters. And then we're solving for N. And I'm just going to move this down here so we have more room. And I'm going to erase and make that better to read. So we're plugging into PV-nRT, solving for the moles of methane. So my volume is 1 × 10⁻³ liters. And then I know R, and I know the temp. So when I do the math, I should get 39.8 moles of methane. So now, in the question, they want the enthalpy change. They want delta H for this much methane. We know delta H for the 1 mole of methane, but we want to know for this volume at this pressure and temp. So I'm going to start with my moles of methane, and I'm going to make a mole. Remember, this is from the coefficient in the balanced equation, and then energy relationship. And again, you can put a negative, or you could give it a negative at the end, because this is how much energy is released, which is the enthalpy change for this particular reaction with that particular amount of methane. So next, I would say those are just, I call those energy stoichiometry kind of problems, or just enthalpy calculations. Now I want to talk about calorimetry. And calorimetry is when we measure heat based on the temperature change of usually water. And different things will respond differently to being heated. Some of them will heat up really fast, some are slow. So we are going to look at that. And then we're also going to talk about calorimeters, and we're going to be doing a pretty big lab with calorimetry too. But a calorimeter is the device that you use to help you to determine the heat that's associated with either a chemical or a physical change. For us, the calorimeter that we use is a simple styrofoam cup, and it works pretty well. Whenever you're doing calorimetry, sometimes you need the specific heat capacity. The values I have over here, you can kind of see, like water has a pretty high specific heat capacity compared to, like, let's say iron. So it takes 4.18 joules to take 1 gram of liquid water and raise it 1 degree Celsius. It only takes 0.45 joules to take 1 gram of iron and raise it 1 degree Celsius. These can be in different units, like kilojoules and kilograms, all different possibilities. But for us, the unit is going to be joule per gram Celsius or joule per gram Kelvin. And a Kelvin degree and a Celsius degree are the same. So when we do our delta T, when we do our calculations, if they're both in Kelvin, just subtract. You don't need to convert them to Celsius. Molar heat capacity is very similar, but it's per mole of the substance. So one other term, and we'll see this in a later calculation, and you'll see that we have 2 different capital C's, but heat capacity is going to be something that we calculate, or it's going to be given in the question. It's the amount of heat absorbed and then how much temperature change there was. So the unit's going to be energy units over temperature units. So there, like I said, there's 2 C's. If you remember MCAT, it's an easy way to remember this equation. In the book, they do an S for the specific heat capacity, just so they don't get the 2 C's confused. But this C is the specific heat capacity, and it's going to always be in, joules per gram degrees Celsius, whereas the other C is in just joules per Celsius. So, and then when we use this equation, Q is going to be the heat absorbed or released. It's in joules. M is mass. It has to be in gram. Delta T is the change in temperature, which would be the final minus the initial. So let's look at this problem. So we are doing a neutralization reaction. We're doing HCl plus sodium hydroxide. It's going to make sodium chloride and water. So I like to draw pictures. So you really have, 50 mils of HCl, and then you're going to add that to 50 mils of sodium hydroxide. So you're going to get 100 mils total of the solution. And we know the density of water is 1 gram per milliliter. So because of that, if I have 100 mils, I also have 100 grams. So we are going to think about the fact that the energy that is released by this reaction, and we know this reaction is exothermic because it's going from 25 up to 31.9, so the energy is getting transferred into the solution. So the energy released by the reaction equals the energy absorbed by the solution. So we're going to calculate that. The energy absorbed by the solution is going to equal the mass of the solution times specific heat capacity of liquid water. So it doesn't matter that it's a solution, that part's negligible. The specific heat will still be 4.18. And then the delta T for the solution. So 100 grams of the solution, 4.18 joules per gram Celsius. And then our delta T is 31.9 minus 25. So it's 6.9 degrees Celsius. So we end up with 2 sig figs, 2,900 joules of energy was absorbed by the solution. That would also be the enthalpy change for the solution would be 2,900 joules. The enthalpy change for the reaction would have been negative 2,900 joules. So I have a second part of the question here. How much heat is released per mole of hydrogen ions that are consumed? So what you'd want to do is write the net ionic equation here. So the spectators, the sodium and the chloride are just spectating, and then it's really just the hydrogen ions, the hydroxide ions that are forming the water. And I want to know how much energy or heat is released per mole of hydrogen ions. So if you look at the question, I'm telling you I have 50 mils of 1 molar hydrochloric. So I can plug into the molarity equation and get the moles. I'm gonna show it with dimensional, but you can sure plug into molarity and solve for mole. So I want to first get into liters, and then I'm going to use that molarity as a conversion factor. So I know 1 mole of HCl for every 1 liter. So that's based on this molarity. And then I'm also going to realize that there's 1 mole of hydrogen ions for every 1 mole of HCl. So that gives me 0.0500 moles of hydrogen ions. And I want to know how much heat is released per mole. So I know that the heat released per mole of hydrogen ions would end up being 2,900 joules over 0.0500 mole. And that would give me 5.8, 10 to the fourth joules per mole hydrogen ion that get reacted. I'm going to do another problem with you. This is a really classic. You did a lab in honors that was like this, where you can take water and put it into a styrofoam cup, and you would know the mass of the water because you know the volume of the water, and it will have a certain initial temperature. And then you can take, we took metal shot, and we had it in a test tube. We put it in a hot water bath, so we got it hot indirectly. So if you add those, you're going to get, that water with the shot, the pieces of metal, and they're hot, they're going to transfer energy into the water. So the final temperature at the end ends up being 18.3 degrees Celsius. I guess that kind of should go over here. So let me get rid of that. Whoops. So TF is, for both the metal and the water, is 18.3 degrees Celsius. The metal was 150 grams, and it was at 75 degrees Celsius to start with. So that was the TI. So in this question, we're going to want to calculate the amount of energy that the water absorbs by taking the water mass times specific heat capacity of water times the delta T of the water. So 150 grams, 4.18. And then the water went from 18.3, it went from 15 to 18.3. So we would subtract 18.3 minus 15. That gives me 3.3 degrees Celsius. So when I calculate this, I get 2,100 joules of energy was absorbed by the water. So we're going to assume that the amount of energy absorbed by the water is the same as the amount of energy that the metal released. You can make that negative if you want. I'm going to just keep it positive. So now I'm going to look at the metal, the mass of the metal, the specific heat, and the delta T of the metal. So I know this value is 2,100. I know my metal mass is also 150. I don't know the specific heat. And then I'm going to do the delta T, but I'm going to do the absolute value of the final temp minus the initial temp. So when I do this, I'll get a positive number. If you wanted, you could keep this negative and not do absolute, and you'll get a positive. But either way, you're solving for specific heat capacity, and those are always positive. Okay, I'm going to keep going. This question, the textbook does it a little differently. I'm going to show you a simpler way to do it. Again, I like pictures. So let's say you have 30 grams of water at 280 Kelvin, and you're going to mix it with 50 grams of water at 330 Kelvin. And my question is, once you mix them, you have 80 grams, and we don't know what the temperature is. Assuming there's no energy loss to the surroundings, what we can do is somewhat like a weighted average. If I know that 30 out of 80 grams are at 280 Kelvin, and then I know 50 out of 80 are at 330 Kelvin. So conceptually, you should see that you have a greater amount of water. So this temperature at the end should be closer to the temperature of the larger amount of the sample. And when you do this, it does work that way. You end up with 311 Kelvin. I'm going to keep going. Here's another one. This is if we are going to react barium nitrate with sodium sulfate. We're going to get barium sulfate and sodium nitrate. And the net ionic, this is the precip, is barium plus sulfate gives us barium sulfate. So in the question, they're telling me that we have 1 liter of barium nitrate, and it's 1 molar, and we're going to mix it with 1 liter of sodium sulfate, 1 molar. And again, I can calculate the amount of energy that the solution gains, because we're at 25 and we end at 28.1. So I'm going to take the mass of the solution. I'm going to use the specific heat of water and the delta T. So the mass of the solution, I know my total volume is 2 liters. And I know that there's 1,000 mils in a liter. And I know the density of water is 1 gram per milliliter. So I really have 2,000 grams of solution. And then, like I said, specific heat capacity of liquid water. And then our delta T is going to be 28.1 minus 25. So we end up, that's 3.1 degrees Celsius. So when I do that calculation, I end up with 2.6 10 to the 4th joule. So the heat of this reaction, the enthalpy of the reaction, is equal to that same value. So that the solution gained 2.6 10 to the 4th, so the reaction must have released that. Let's put it in kilojoule too to make it, less, not having to use the power of 10 and all that. So in the question, they want to know the enthalpy change per mole of the barium sulfate that's formed. So what we want to do is use that net equation, the net ionic, and then we're going to use our molarities and liters of each of the reactants to solve for the moles of those. So what I mean by that is I would take my 1 liter of barium nitrate and I would multiply by that molarity. And then I know that I have 1 mole of barium ions for every 1 mole of barium nitrate. So that gives me 1 mole of barium ions. So similarly, I'm going to do the same thing, but now for the sodium sulfate. And I know the molarity. And I know that I have 1 mole of sulfate for every 1 mole of sodium sulfate. And I know they're the same, but they don't always have to be. So you technically, I'll just leave it at that. But so really, if you go back up to that net ionic, you can say, oh, well, I have 1 mole of this. I have 1 mole of this. So they're perfectly in the right stoichiometric ratio to give me 1 mole of barium sulfate. So I'm going to take my energy, that the heat of the reaction that formed the barium sulfate, and I'm trying to figure out per mole. So it's really going to be negative 26 kilojoules per 1 mole of barium sulfate formed. So it's negative 26 kilojoule per mole. Oops. During class, I asked people to try to do number 1 on the WebAssign. You would also be able to do number 2 because I did a problem similar to that. So if you want to take a break and do that, you sure can. I'm just going to do a couple more problems. This is just the solution to the one we just did. Just talking about bomb calorimetry, this is when you take something, you burn it inside of a calorimeter where the volume of that calorimeter is constant, unlike the styrofoam cup that has an open lid. This is constant, so the work, there is no work being done. So if I do a question like this, if you read this pretty long question, this is getting at looking at methane as a fuel source versus hydrogen. So this time we're given the heat capacity, not the specific heat capacity, but this is C. So if I want to know how much energy is released into the calorimeter from the methane, I'm going to take, so it's really the amount of energy from the combustion of the methane is going to equal that heat capacity value times the temperature change that resulted from the methane, which was 7.3 degrees Celsius. So when I do that, I get 83 kilojoules. So by burning 1.5 grams of methane, it released, it went up in temperature by 7.3, so it released 83 kilojoules. Similarly, we can do Q for the hydrogen by using the heat capacity of the calorimeter and multiplying by the temperature change of the hydrogen. And we get 162 kilojoules. In this question, it's still really not possible to compare them because they weren't the same size sample. So what we really want to do is figure out how much energy is released per gram. So that would end up being, for the methane, it would equal 83 kilojoules per 1.5 grams of methane that were actually burned. So that would be 55 kilojoules per gram for the methane. And for the hydrogen, it's going to be 162 kilojoules divided by the mass of the hydrogen, which would end up being 140 kilojoules per gram for the hydrogen. And let's keep going. We're just going to talk here now. So I would read the question, think about it, and then you can look at the answer, unpause the video. So 2 different metals of equal mass have different heat capacities. That would be like iron maybe and copper. Which undergoes the smallest change in temperature? That would be the metal that has this, the higher heat capacity. So if something has a heat capacity of 0.5 versus something that is 0.1, this one takes more energy for it to take a gram of it and raise it a degree Celsius. So it's not going to heat up as quickly, assuming equal masses and equal amounts of heat. Next question is similar to kind of like one of the questions that we did, actually not so much. If you have 50 grams of water and it's at 80 degrees, and you mix it with another 50 grams at 20 degrees, the temperature is going to be somewhere between 20 and 50. Oh, just wait. Oh, sorry. I'm on the wrong question as I'm looking. So we have equal masses of water. So this is one where we don't need to do that weighted average like we did. We just know that the temperature is going to end up somewhere between these, probably about equal. So the temperature is going to result in a temperature maybe around, somewhere between 50 and 80. We'll leave it at that. This one is different now because this is the one where you would want to kind of do the weighted average, and you could just do it in your head if you wanted. I can show you again if you want, like 50 grams and 100 grams. So we know we have a 150 gram sample or total. So it's kind of like 1/3 of it is going to have a temperature of 80, and then 2/3 of it, so 100 grams out of 150, is going to have a temperature of 20. So you know your resulting temperature is going to be closer to 20 than 80. And the correct answer here would be A. And in fact, when you do this, I think you get like 40. So the temperature is going to be closer to the one that you have the most of. And you have 100 grams compared to 50. This one, you have 50 grams of water at 20. And then you have a 50 gram sample of iron at 80. So they want to know the final temperature of the water. So the metal is going to heat the water up, but the water has a specific heat of 4.18, and the iron is 0.45 joules per gram degree Celsius. So the water is going to heat up, but not as much as you would think. So you'd want to pick A because it has a higher heat capacity, specific heat capacity.